So the last speaker for the session is Brian Rice, and Brian is actually a postdoc research fellow at Colorado State University, and I apologize for that mistake I made it earlier. Brian is going to talk about the flywheel genomics leads to efficient trait architecture dissection and rapid local adaptation. Thank you.
No, yep, there we go. I'm aware that I'm between you guys and lunch, but I hope this gets some appetite going. So, first of all, thanks to the committee for recognizing my abstract and inviting me to talk. This is my first time in NAPB, although I've definitely been working in breeding or breeding adjacent for like the last 10 since I started college. So I'm surprised I haven't been here. You guys got a lifetime member now. So. Today I'm going to talk about this relationship between genetics and breeding and my philosophy on it. So took a stab at describing the purpose of breeding to release varieties. Breeding is very good at this, and I took a stab at describing the purpose of genetics, and from a non-applied perspective, we're producing knowledge, right? And oftentimes in crop genomics, what are we using to do this? We're using the global germplasm, the varieties that breeders have provided us, the land races that we have from years of breeding in whatever crop you're working in. With my lab, we work in sorghum. So we take the varieties, we do some sort of mapping. I'm trained in quantitative genetics, so this is what I work in, and we put out some sort of knowledge, dissecting some trait using this global sorghum, this diversity. But what I ask myself is if this is an efficient way to do an applied science. If to take this diversity that isn't a breeding program and try to apply it to a breeding program. I've done it. These are studies. These are my own studies using mapping populations, and I've said in the papers, this is supposed to help breeding, or if we study this trait, it's going to have an impact on plant breeding, right? But is this an efficient way? This is different mapping populations, and this is some criteria that I came up with to describe and rank these different mapping populations and how they fit this criteria. And as you can see, I made it an ideal one, and none of them really fit this ideal one. In particular, none of them, I think, fit the transferability to breeding programs as well as we'd like them to. The other big issue with a lot of them is confounding structure. It causes us, even if you have a QTL that you like, you have to put it in your breeding program and reevaluate it. A lot of GWAS hits just go unnoticed because it's going to take time to evaluate them in your population, and there's a good chance, even if they were a real hit, they're not adapted to your population. So this is the framework that I want to push. Is this framework where breeding and genetics are working much closer together. And so how does that look? Well, from breeding programs, breeders, I'm not a breeder, I'm breeding adjacent, I'm a geneticist, but I talk to breeders, I work with breeders, they're the ones who know what their roadblocks are, what are the issues that are going to actually most impact their breeding program. And then they also have the data. They've been selecting on the traits, they've been working with the traits, they should have the data for me to work with. All right, and then in return, not only do I get to put out the knowledge, the basic science, the basic science stories, but I get to provide them back technology, right? Whether that's markers to select on, whether that's adjustments to their breeding schemes. We get to provide them back technology, or maybe they need a new phenotyping technique because the way their phenotyping isn't heritable. We provide them back this technology, and this relationship is cyclical. So I'll give an example of what this looks like in my own research. So my program, we work with a breeding program in Haiti, and in sorghum right now, you can't breed in Haiti, grow sorghum in Haiti without resistance to sorghum aphid. There was a major biotype shift and an outbreak in Haiti, and in B there, that's the production tons, and basically went down in 1 year. And the breeding program was forced to start selecting, and they started some recovery. From that selection, we were able to go in, with their genotypic data, compare it to global sorghum, and see that they were selecting hard at this one loci, which happened to be really the only known loci for sorghum aphid resistance. Then from there, they developed the markers. They were able to select on the markers, and we also were able to get those markers into global sorghum. So what did we do? They had issues. They had roadblocks. They needed a selection method. Right? They wanted to know what was providing the resistance. They gave us a population that was under very intensive selection. We did the architecture dissection and provided them back the technology. But it's iterative. So now what we have is this is the population structure of the breeding program. The big teal one here, this is the main recurrent selection population that's fixed for this loci now. So mass population fixed for this loci, and then to bring anything into the population, they cross it with things from the main population and then have to screen it. Like I said, without the RMES1 positive allele, everything dies without being sprayed. It doesn't grow past a foot tall. So you have to do this strategy. But now what we have is we have an F2 mapping population, multiple F2 mapping populations, as well as this massive populations fixed for RMES1. And so now we're able to go back, take this data, address a new roadblock. Is the resistance monogenic? What does the breeder need to do? There's going to be another biotype shift. What do they need to do? And this is just a list of tools and analysis that we've been able to do with them using these populations. And I'll just show one slide showing what we've actually, part of what we've done. So we did a GWAS on some of their traits, well, the F2 mapping populations. And what we got is as expected, we expect RMES1 to be segregating. It was segregating and significant. We also, while we were doing the GWAS, somebody published a pretty nice paper describing this SB Werke gene and showing that it was provided resistance. We went and looked in our mapping population as well as if it was under selection in the main population, and sure enough, the breeder was selecting on it. We found that it was significant in the F2 mapping population. So very quickly, we gave the breeder information. We were able to provide information to the community, supporting the theory that this gene underlies resistance. Yeah, and then like I said, main population's fixed, so now we have variation that we can actually, that's now significant, that wouldn't have been significant when RMES1 was segregating. And we can compare regions under selection with our association studies to prioritize new candidates. So the cycle continues. We asked ourselves, is this relationship, is this the success we had with this breeding program, is it due to chance? Right? Or is this population better positioned for it? Right? So I came up with a criteria. If we want to do this flywheel genomics, it has to benefit both genetics and the breeding. So you can create mapping populations, but it doesn't benefit the breeding program. Breeding program can maximize genetic gain, selection schemes, but that might not benefit genetics. So we did some simulation studies, just comparing two different breeding schemes, biparental family selection and recurrent selection, and then I simulated two traits, one where we have a trait under selection and one with a trait that isn't under selection. And first, what we see is that the recurrent selection is maintaining genetic diversity, again, and then as well as still keeping genetic gain. It was kind of cool yesterday to see this exact plot from 1960 or so, 1970, the simulation study that was shown in the very first talk of the conference. So updated simulation still holds true, recurrent selection works. And then also the traits not under selection, you're not losing phenotypic mean, you're not losing diversity in those traits as much. And the other thing too for mapping, we're not getting as hard as selective sweeps. This is minor allele frequency at a QTL under selection, and we're not getting as hard selection sweeps, and this holds true also for QTL that aren't under selection. Different breeding schemes are going to fix those compared to other breeding schemes. And then for this type, because you have diversity, when a new stress comes in and you have to start selecting for the stress, that's what's signaled here, and that's what happened with the sorghum aphid. You have the diversity in your population already to start selecting. So again, we're benefiting the breeder and the genetics. So, two key takeaways that I hope is what I'm trying to get across. Breeding populations should be used to do trait genetic architecture dissection. And this is going to work best in this flywheel genomics analogy if the program is both trying to maximize recombination rates, so that's what recurrent selection should do, and maintain diversity, right? And hopefully I showed that this is going to benefit both genetics and breeding. Yeah, so this is the flywheel genomics in its, without a specific example, just a framework. If you want to look at this circle more, poster 122 is up. And then if you want to know when I publish this actual paper, you can follow me on Twitter. Sometimes I post quirky opinions on quantitative genetics on there as well too. So, lastly, this type of flywheel genomics, the type of intensive collaborations I'm proposing can happen, but they take dedicated individuals, both from the breeding side, a breeding program at the University of Kinsea in Haiti, and then our genetics lab. We're not a breeding lab. We have to set up this collaboration in order to do this type of thing. And then it takes funding. I think this framework has the potential to benefit small shareholder farmers around the world, small breeding programs that aren't being served by, that aren't being as directly served, as directly worked with. I think they have this benefit, but that's going to take funding. So, yeah. And with that, happy to take questions.
Any questions? Well, everybody looks like looking forward to lunch, but
Question?
and any questions? Okay, no. Okay. Please join me and Artie in thanking all the speakers in this session. Okay.